Good day, people. So I hope you enjoy your Easter holiday. So today we'll be looking at work, energy, and power. Right. So welcome back. Alright. So I want to divide this work into 3 or to 4 parts. Whereby first, basically we're doing calculating the network done. Then maybe the following one we will be doing the energy principle, and then the last one will be in power. Right. Anyway, let's quickly look at work until we able to calculate the net work done. Right. So here we have a definition of a work done on an object by a constant force. What? By a constant force. So we see that a W is equals to F delta X cos theta, where F is the magnitude of the force, delta X is the magnitude of the displacement, and theta is the angle between the force and what? And displacement. So when you do a work on an object, that object basically it must move or it must come to an end. So we're able to discuss it that way. So remember that our force, right, this will be the force, the delta X that it will cover, and the theta, it will be the angle that is between the force and the displacement. And also remember that when work is done on an object by a force, the energy is transferred from one object to another object. This is how energy transfer takes place within a system, and the amount of work done by a force is equal to the energy transfer taking place. So basically meaning that a work done on an object is equal to the energy transferred. Hence, our SI units for work, it will be what? It will be joules. So work done on an object is same as the energy transfer that is taking place. Alright, and also we have types of work done. Remember that work done can be positive, zero, or negative, depending on the angle between the force and the displacement. Alright, so here is displacement. Remember we use delta X to represent displacement. Sorry for that. Alright, so here we have a positive work, so I want to say positive work. So when we do a positive work, meaning that our angle must be less than 90, and we're going to have a positive work. And then in terms of energy, it means that here in a positive work, we are transferring energy to another object. And then, for example, maybe you are pulling a box. If that box moves, it will cover a certain delta X, and then also you pull it at an angle. So therefore, you're gonna do what? Positive work. And if you are pulling that thing and you're gonna hear a sound as you pull, that sound is the energy that you are taking. This energy that is transferred from one place to another. That's a energy that you are going to share. That means that energy is what is being transformed in other form of energy. Right. Then now here we have a zero work. It's like a zero work. The angle there it must be 90. Then you're gonna perform a zero work. So if you have a wall and then you are pushing the wall and the wall doesn't move. So if the wall doesn't move and also you are applying a force to your wall, and it doesn't move. It means that your force, you are applying a force at an angle, right? And once you got cos 90, you'll get 0. Alright, if there's no displacement, meaning that you can see the force multiplied by, if there's no displacement, meaning that 0, and then you get what? 0. So when you do, when the angle is 90, that means that you're going to have a what? A 0. And also from going forward, when we do the calculation, because it's very important for you to draw a free body diagram so that you can see the forces that act on an object. But once we see that, okay, this force, it is perpendicular to the surface that I'm dealing with, then therefore I know that I will have a 0 work. So we're going to exclude that. So once you see a force that is perpendicular to the surface, it's going to do a 0 work always, because what, the angle there will be what, 90. Okay, then here is when we are having a negative work done. Okay, so meaning that our angle will be greater than 90. So once our angle is 91, they start to be what, negative, because of now the direction of the force and the direction of the displacement are facing in the opposite direction, and hence we're getting a negative work done. So let's quickly look at how we calculate the work done on an object. Okay, so now there we can see that we have A. They say that we have a 0.12 kg ball that is thrown vertically upwards as it reaches the height of 4 meters. So we have to calculate the work done by the gravitational force on an ball. So let's draw a free body diagram. So remember that we know that our FG will always face downwards. That's the only force that's taking place. But also you must put into consideration where does your delta, your object covers your delta x, right? So here, because they say that you thrown this ball upwards from the ground, okay, and then your FGQ, meaning that it will covers the displacement in positive direction. Here is what displacements in positive direction. Let me use dotted lines to represent this one is our delta x. Okay, and also you can see that our angle now, it will be what, 180, because angle on a straight line are equals to 180. So let's quickly calculate the work done by the gravity. So that it will be what? Remember, work is equals to the force delta x cos of theta. Now here we're gonna say the force, that one is what? Fg what? Delta x cos of theta. Now remember, our Fg is what? It's going to be the mass and the gravity, acceleration, and the delta x and the cos theta. Then our mass there is how much? Is 0.12 multiplied by 9.8. Our delta x is 4 meters. Is fine, and then also cos of what? Cos of 180. So cos 180 basically is -1. So it is -1, therefore meaning that you're gonna have a negative work done that is caused by the gravity. So the work done by gravitational force, it will be -4,704 joules. Remember, our work done is in joules. Let's quickly look at letter B. Here it is. Allow me to change color. Right. So B, we have a Futuro. I don't attempt to push my car in order to start it. The Chiro apply a horizontal force of 300 newtons to the car, but my car doesn't move. Now, when you look at this, Romavinga, the first silo hearing how much work is done on Vichero, on how much work is done by Vichero on the car. So they say that Vichero apply a 300 newtons force on my car, and that car, it doesn't move. So how much does the work done, how much does work done, yes, how much work is done by Vichero on the car? So if you are doing a work on an object and it doesn't move, it means that you are applying a force at an angle. Yeah, we are applying a force at an angle of 90, or there's no displacement, meaning that your displacement is 0. So once you multiply everything there with 0, you will get what? 0. So the work done by 0 on the car, it will be what? It will be 0. What? Joules. Okay. So now, what if Vichero and his friend Katlero, now they're able to push my car, right? Meaning that now each of them they exert a force of 300 newtons, right? So once each of them exert a force of 300 newton on the car, and that car moves and covers what? 50 meters. Now we must calculate the work done by learners on the car. So first thing, they say that each of them they exert a force of what? 3,000 newtons. So meaning that the force of a learner's it will be what? 3,000 times 2, which is 6,000 newtons. So basically, there is a force that the car experiences, right, which is 600 newtons. And then that car, it will cover what? 5 meters, right? Now we must calculate the work done by the learners on the car. So basically, we're gonna say work done by the force of applied, because they are applying a force on the car, which is with the force of applied, then your displacement and the cos of that, cos of theta. So let me draw a little bit of diagram. Let's say we have a car here, right? And then you push this car, right? So when you push this car, mean that you exert a force in this direction, so that will be a force of what applied. But also your delta x, it will covers a direction of your force applied, and that means that your angle there is going to be 0. Right, then the force applied there that you're gonna use, you're gonna say 600, then the delta x is how much? 5, right? And the cos of what? Cos of 0. So cos of 0, it will make our work to be what? To be positive. So work done by the learners on the car, it will be how much? 3,000 joules. So now here we're gonna be looking at how we calculate the network done, right? And we know once we say the net, it means that, remember in Newton's law, once we say the F net is close to meaning that you have to add the forces that are taking place on, or rather that are acting place on the object. So to calculate the net work done, you calculate it in two ways. The first one is when you calculate when you sum up the individual work, meaning that we have the first work done, second first work done, meaning that maybe I can have work done by FG, work done by FK, and then I want to add them to have what? Work net. Or I can use work done by the net force. Net force, how? When you have what? When we are dealing with a constant velocity, meaning that you're going to say that the F net is equals to 0, whereby now you have to state those forces. Remember that you take the positive one first, we're going to minus with the opposite one that is acting in the opposite direction. Let's say now we have a force applied, and or maybe the FK is in the opposite direction. So meaning that your F net will be equals to FA minus FK. Alright. So this is how you do work done by net force. Only if you are dealing with what? A constant velocity. They basically tell you that you are dealing with constant velocity, or sometimes they will just say something is rolling on its own. Then mean that constant velocity is there. Right. So let's quickly look at this example. They see that a car accelerates from rest to the left between the two traffic lines. So please, I made a mistake here. I just realized now. So this car basically, they say that it accelerates from rest to the left. So basically from here to the left. So basically this front, you must face that way. So you're gonna take it if this car was reversing. Okay, that's fine. Then which it is 40 meters apart, the car engine exerts a force of what? 1700 newtons, and the car experiences a frictional force of what? 650 newtons. 50 what? Newtons. So let's draw a free body diagram first so that you can understand. But when you draw the free body diagram, if they say draw the free body diagram, you must draw all the forces that are taking place on an object. I guess both normal force and Fg. But now we know that the forces that are act perpendicular to the surface, they will be equals to what? 0. So in order to not waste time, even though they didn't say draw the free body diagram, just draw your free body diagram for the forces that are taking place. So we have the force of the engine. So allow me to write the F of E, and the force of what? Fk of the friction. Okay. So meaning that the car is going in that direction, and it covers the 40 meters in that direction. So meaning that our delta x is covered in a direction of what? Force of the engine. So meaning that the force of the engine and the delta x, the theta there will be what? 0. But for the Fk and the delta x, it will be how much? 180 degrees. Okay. So let's calculate the net work done on the car. Right. So basically, here you can see that we're going to use the first one whereby we sum the individual work. So we're going to start with the force of the engine, whereby is equals to the force of the engine, delta x, cos of what? Cos of theta. Then the force of the engine, it is 1700, the delta x, which is 40, multiplied by 40, and then the angle there is 0. And then we're going to have how much? 68,000 what? Joules. Okay. Then let's calculate the work done by what? By the fraction. The work done by fraction, it will be the fraction, the delta x, and the angle that is between delta x and the fraction. Then your Fk is 650, delta x 40, that will multiply by cos of what? Cos of 180. And hence we have what? Negative, right? Because of the cos 180, that means that the fraction is doing what? A negative work on an object. So when you punch in the calculator, you get a negative 26,000 watt joules, right? And then you're gonna say work net is equals to the work of what? The Fe plus the work of the Fk. And then therefore the work on the engine is doing 68,000 plus, remember this one is negative, we have to put bracket, and then it will be negative 26,000, and then you know positive times negative, it is negative, meaning that you're gonna say 68,000 minus 26,000, and we are getting how much? 42,000 joules. So that is the work net that is taking place on the object, on the car. So let's quickly look at the second example. Then in a second example, allow me to use a different color. So let's say we have, suppose that the driver of the car applies the brake over a distance of 20 meters as he approaches a red traffic light. The brake exerts a force of 2,200 newtons and a frictional force of what? 800 newtons. So in a diagram, you can see that when you draw the free body diagram, because he applied a force, a brakes. When you apply a brake, basically what happens to the car? The car reduces what? Force. It reduces its speed. So it means that when you apply the brakes, the brake does what? It pulls the car in opposite direction, right? So hence, we're gonna say the force of the brake, okay? And also you're gonna have, they say that you also experience a force of what? Force of fractional force. But remember that also the delta x is covered in what? In the opposite direction. So it means that the angle that you're gonna use there for both the force of the brake and the force of the frictional force, it will be 180. So we're gonna start with work done by the brake. It will be the force of the brake delta x cos of what? Cos of the filter. Then your force of the brake is how much? 2,210 newtons. Delta x is 20 cos of what? 180. Then how much are you getting there? Getting negative. You're getting negative 44,000 watt joules. Then now let's quickly look for the work done by the frictional force. So work done by the frictional force will be the frictional force, the delta x, and the cos of what? Cos of theta. Then it will be 800 delta x, that is covering 20 cos of theta, cos of 18, right? And then you are getting negative 16,000 joules. Then now when you look for the work net, it will be how much? Work net by the force of the brake plus the work net by the Fk. Now the work net by the brick is negative 44,000 joules plus, also put bracket, minus 16,000. So basically going to be what? Negative 44,000 minus minus 16,000, right? So basically we're going to say minus there, and we're getting minus 60,000 joules. That's how we calculate the network done by different forces that is acting on the object. So number 3 is really important. Before we go there, let's quickly look at now. Remember, in straight line, if we have in this object, remember object in a, let's say, a flat surface, remember that I said the forces that act perpendicular to your surface, they will do what? They will they can really cost 90, and then they will produce what? A 0 work, right? Jano, if which are the normal force and the gravitational force. But now we in the incline. So the normal force still, it will do what? It will do a 0 work net. Why? It's because of what? It's because of the normal force is always perpendicular to the surface. So it's going to do a work net. A work net, the 0 work net, right? Then now remember on the Fg is always what? Downwards. Again. So the Fg is always downwards and it's not acting perpendicular. So now the Fg in incline, we can able to get the work done by the Fg in incline only. But if we have a rough surface like this one, it means that our work net by, work done by gravity, it will be 0. But once we move from inclined plane, our work net is not, by gravity is not 0. And there are 2 steps in order to calculate work done by the fractional force. The first one, you're gonna resolve your Fg, Again, you're gonna have what? Let me change the color very quick. You know that you're gonna have Fg perpendicular and Fg parallel. Again, but you know that I say that angle that act perpendicular to the surface will produce a 0 work done, as well as the Fg what? Perpendicular, meaning that we have what? Fg parallel. Okay. So meaning that you can see the work done by the fractional force, that it will equals to what? Fg parallel and delta x cos of what? Cos of 0. And our angle there always use between 180 or 0. Then also remember when Fg parallel, it have Fg sine theta. Now remember, now we have 2 thetas here. Remember, this angle is the angle of your incline. Then the cos theta is the angle that is between your what? Your force, which is the Fg parallel, which is going downwards, as you can see. And if this meant, I think, is going downward as you read the equation, then you can see that now you're able to use in the cos, you're going to use what? Cos 180. So the first one, let me write it clear. You're going to use the work net by the gravitational force as Fg parallel delta x cos of 0, cos of theta. Then also you're going to use Fg by the force of gravity, work done by the force of gravity, we're going to say Fg, then you can say delta y cos of theta. The reason why we say delta y, when you look at your free body diagram, your delta y normally is your opposite side. So meaning that we have to go and look for this opposite side, this one. That's how we calculate the work done by the gravitational force. Then now let's quickly read the equation. It's saying a man pulls a cart with a load up a hill which form an angle of 25 with a horizontal. Right. The mass of the cart and the load is 350 kg and the frictional force of the road of the cart is what? 180 newtons. He walked a distance of a half at a constant velocity, except that the gravity remain unchanged. So let's quickly focus on delta x, because they say that he walked what? A 1 kilometer, half a kilometer, sorry. Meaning that you know that 1 kilometer, it consists of 1,000 what? Meters, because we are working with what? Meters. So if they say a half, it means that you're gonna have what? A half of what? Half of what? 1,000 meters, which is 500 meters. So our delta x, it will be how much? 5,000 meters that you are going to use. Yes, that you're going to use. And then now we see that we have force of what? Fk is how much? 180. Okay. So 3.1 say that we must draw the free body diagram for all the forces that are acting on it, that are taking place, that are acting on the cart with its load. So the 3.1 we can normally say we can start with the normal force, right? Remember the normal force, and then our Fg. Okay. Now we have a force of applied because the man pulls the cart what? Up. So we're gonna have what? Force applied. And also this cart and load, it experience a frictional force of what? Of 180. Then we have a force of what? 180. So it's a force of what? Frictional force. This is what you draw, but remember, when you do the calculation, you must put in mind that you also have to resolve the Fg into what? Its component. That means that we have Fg what? Perpendicular, and we have what? Fg parallel, and we have what? Fk. This is what we use in what? Calculating in Newton's law, right? Same here, you're gonna use it, but you're gonna focus on Fg what? Parallel. So 3.1.2 determine the net work done by the cart and the load. So the net done by the cart and load, you can see that because of we have a constant velocity happening there. So therefore the net work done by the cart, allow me to write it here, going to be 0 what? Joules. Right. Now how will you 3.3 say that you must calculate the work done by the man, which thus on the cart and the load. Basically we're going to look for the force of the applied. Right. Remember also we say that the F, if constant velocity, you can basically say a work net is equals to 0, meaning that we have to go and look for the work done by the Fg parallel, and also work done by the work done by this force applied, right? and also work net by what? Fk, because the only forces that's taking place are 3 forces, as you can see in the free body diagram that you normally use when you are calculating. So let's look for the force of what? So 3.3. Remember the work net is equals to 0. But let's quickly focus looking on the work done by the Fg, which will be the Fg what? Parallel delta x cos of what? Cos of theta. Then the mass of the object we know is 350 by 9,8. Sine of what? The sine of the angle, which is what? 28. Delta x, that is covering half a kilometer, which is 500. So we're going to multiply by 500, and the cos of what? Remember, the displacement is covered going up the hill, so you can see that is 180. Right, it's 180. And when you look here in the graph, you can see that this opportunity site is your what? 500 meters, or your displacement. So if you're using another work by Fg, so we have hypotenuse, and so this angle is opposite to this side, and therefore you can normally use sine. Maybe you're gonna say sine of what? Sine of 25 multiplied by 500 to get what? To get this opposite side, whereby is the one that you're gonna use here in your delta y. Remember, is what work done by Fg, that is close to Fg delta y cos of theta. So your delta y that you are finding here, remember, is delta y, that is equals to sine of 25 multiplied by 500. So that delta y that you found, you want to substitute here, and a cos of what? Cos of 180. Okay, then I believe you get the same answer as negative 724,790,32 joules. That is the work done by the gravity. Then the work done by the Fk is how much? Fk delta x cos of theta. Then the Fk is how much? 180. The delta x is 500. Cos of what? When you look at the cos of 180. Okay. Then how much are you getting? Negative 90,000 joules. So do we have the work, or we don't have the work done by the Fk in which we are looking for it? Okay. Then remember that we say that the F net is equal to 0, meaning that we can say that, and also remember the work net will be equals to work net by Fg plus work net by the Fk plus work net by the force applied. And then you can simply say that our work net, it will be 0. That is because of where we see net, you can substitute it with 0. Then you're going to have work net of Fg plus work net of Fk plus work net of Fa. Sorry. Then work net by the frictional force is negative 724,790,32 plus by the work net by the FK will be negative 90,000 plus work net by the force applied. Then basically we can transpose our work net, or we can transpose this figure when you punch it in the calculator, right? So when you transpose that figure, it will be how much? It will be 104,790,32 joules, right? That is equals to the work done by the force applied. But we're not looking for, I thought we were looking for the force applied by the man. But 3.3 say that we're looking for the work that the man does on a cut and a load. So the work that he does on a cut and a load is 800,414,790,32. The work done by the force applied is 800, that figure. So the work done is 814,790,32 joules. Then let's quickly look at the last one. So we can see that they say that Katlego there, that's what Katlego is a free-wheeling a bicycle down a hill, right? Now that hill form an angle of 15 degrees, to the horizontal. The combined mass of Katlego and her bicycle is 90, and the frictional force of the road on the bicycle is 70 newtons. Now we must calculate the distance that he covers while he goes up to the bottom of the hill. If the net work on her and her bicycle is 300 joules when he reaches at the bottom of the hill. So we can see that you are given a net, how much? 3,000 joules. Then you are given also the FK is how much? 70. Then when you draw a free body diagram, we can see that the FG parallel is also taking place there, and also what? An FK. And also when you look at the diagram, you can see that the FG parallel is the same direction as your delta x, but opposite direction is what? FK. That means that FK is 180, then FG parallel is what? Is 0. So basically here we can go from using constant velocity 1, remember, whereby we can say a work net is equals to the F net delta x cos of theta. Remember? But now let's go and look how we get the F net. Remember, the F net, it will be 0. So now the FG parallel, because the motion is going down, so it will be positive minus what? Fk. Then you know mass will be what? 90 multiplied by 9,8 again. Then we're going to say sine of what? 15, sine of the incline. Right? And then minus Fk, they said is how much? 70. And therefore the F net is how much? and the Fnet is 159 newtons. That is your Fnet. Now when you go back, we can see that worknet is given. We looked for Fnet. We know the cos theta. So if our Fnet is positive here, can it mean that cos what? Cos 0. You know? So if we found that our Fnet is negative, it means that we're gonna use what? Cos 180. So our work net is 3 joules, not 3 joules, 3000 joules equals to the Fnet 159 delta X is what we're looking for, and then we have what? Cos of what? 0. So cos of 0 is 1, right? So it means that we have 3000 that is close to 159 delta man X. Then we're going to divide by 159 both sides, and you get what? Delta X that is close to what? 18,9 meters. So that is your delta X. So that is Cutler-Hawse delta X that you will cover as you go what? From the top of the hill, to the bottom of the hill, he will cover what? 18,9 meters. So coming to the end, this is our end, how we calculate the network done by the forces. Next video, we're gonna look at energy principle. We're gonna look at energy principle, work energy theorem. Then from there, we look at the equation. Thank you.